Good afternoon and welcome to Orkney International Science Festival 2022 in this, Scotland's Year of Stories. My name is Eric Walker and it's my pleasure to be hosting this session both in person here in the Orkney Theatre and also online via YouTube. Our speaker today is local man Professor Tom Stevenson, who has a 100% record of attendance at the Orkney International Science Festival since 1991. Tom retired at the end of 2012 from the University of Edinburgh, where he held a personal chair in microelectronics technology and was Operations Director of the Scottish Microelectronics Centre. Prior to joining university in 1980, he had worked for Ferranti Limited and Wolfson Microelectronics. Born and brought up in Orkney, he attended Stromness Academy before going on to study physics and instrument design at the University of Aberdeen. He had the privilege of being taught by Professor R.V. Jones, who had been an advisor to Winston Churchill on scientific intelligence during the Second World War. Tom has been involved with the Museum of Communication in Burntisland, Fife for over 20 years, having been a colleague and friend of the founder of the collection, Harry Matthews. It's 100 years since the BBC's transmissions from 2LO started public service broadcasting, and today Tom is going to tell us the story of early radio and shows us it in action. I want to encourage everyone watching, both here in the theatre and also online, to take part in this event, and ask you to please enter your comments and questions in YouTube's live chat or using the app Slido. If you look up on the screen, you just simply point your smartphone or your tablet camera at the QR code on the screen and it will take you to the question and answer area. Or you can visit www.slido.com and enter the code 3435541. Then you can easily enter your questions and answers. However, for those of you who are uncomfortable with that here in the theatre, we'll also be passing the microphone around the audience in the old-fashioned way. Communications technology is a wondrous thing, and we're just about to find out some of its beginnings. Tom, over to you.
Thank you very much, Eric. Thank you. Well, I think after that introduction, you're bound to be disappointed. However, going on to the first slide, Howie has come up with an intriguing title as usual. It probably makes no sense to you, but I'm hoping that by the end of this talk, all will become clear. It's good to see such a good turnout of a live audience, and I would like to give a special welcome to those who are viewing this online, wherever you may be. I just hope that your weather is better than it is here in Orkney, which is wind and rain and thoroughly unpleasant.
Summertime.
Summertime, yes, okay. Anyway, before we go any further, I would like to assure you that no cats were harmed in preparing this lecture. Now, Eric mentioned, and Howie has mentioned in the publicity, that I would be demonstrating radio technology today. This came about as a result of a phone conversation with Howie early on. I thought it'd be fun to have an old crystal set and plug it into the audio system in the theatre. But when I thought about it a bit more, I thought, nah. So I chickened out. And the reason is that if you look at the outside of this building, it's quite high. And for a crystal set, you need a long aerial, perhaps a quarter of a wavelength. And that would imply sending Nori up on the roof with a drum of cable and getting to string it from the aerial that you see there to a lamppost across the playing field, something like that. And I thought this was unreasonable. So instead, I'm using a radio mic. This is a picture of it. So the microphone here is connected with a wire to a transmitter that's in my shirt pocket. And that is sending a radio signal at very high frequency, in fact ultra high frequency, to a receiver, which is in Norrie's control room up at the back. And because it's very high frequency, the wavelength is very short, 347 millimeters. So a quarter wavelength is about 80 millimeters. So the antenna here is just a wee stub. Now this lecture is the latest in a number of joint lectures that we've done with the Orkney Wireless Museum. In fact, since 2012. This is a slide that goes back to 2012. And I'm really grateful to Peter MacDonald and his colleagues at the Orkney Wireless Museum for a lot of material that is in this lecture. This is the Museum of Communication in Burntisland, where the theme of this year's exhibition is 100 years of public broadcasting. Now, when I looked at the scope of the subject matter, my first thought was, oh heck, how can I possibly do that justice in a 45-minute lecture? And then what saved me was I noticed in the programme that it said, this is Scotland's Year of Stories. And it's also the centenary of the BBC. So rather than trying to cover everything, I thought, I'll just pick a few stories. Some of the stories might be about physics or technology, because it is a science festival after all. And some of it about the personalities involved, and some of it about early radio in Orkney. So, here we go. A few stories. Crystal sets, the basic physics of radio waves, some of the key inventors and scientists like Faraday and Maxwell and Hertz and Marconi, of course. Early radio in Orkney, some technical developments, and I'm going to keep off microelectronics, just in case I go into verbal diarrhea about it. And give you a few pointers to the future, how broadcasting might change, might have to change. So I found these publications really useful in preparing this, apart from the internet. The book on the left is brand new this year, and it's a very thoroughly researched piece of work on the history of the BBC, all aspects of the BBC, by David Hendy. And the one on the right dates from 1981 and was written by James MacDonald, who set up the Orkney Wireless Museum. And that is really good because it includes names and details of local worthies who were radio enthusiasts or dealers who sold radio and that sort of thing. So, with that preamble, I would like you to go back now to 1922 and imagine that you are trying out this newfangled radio for the first time. So this is a picture of an exhibit in our exhibition at the museum in Burntisland. This gentleman here has a crystal set on the table in front of him. You'll notice he's wearing headphones. He doesn't have electricity in his house. And he's darn cold because he's wearing a bonnet and a scarf and a jacket indoors. Now, he's got a very long external aerial there, and that is connected to the crystal set, as is his headphones. There are no batteries involved at all here. The crystal set has a couple of very simple control knobs on it for tuning to select the station, and in the top center, it has a very critical device, the detector, which I'll talk about some more. Now, a remarkable number of these 100-year-old crystal sets still survive in museums and collections and so on. This is an example from the Orkney Wireless Museum. There are 4 commercially made receivers there at the top, and there are 2 homemade ones down here. Now, when new technology comes in, very often the commercial supply can't meet up with the demand. And under these circumstances, enthusiasts tend to build their own. This happened again in the 1980s, for example, with home computers. Some people built their own from kits. So what did a crystal set consist of? Well, it was remarkably simple. Here's a diagram from Wikipedia. A long wire antenna outdoor, which is connected through a tuning coil or something like that to ground, and the signal is tapped off into a detector which feeds headphones. Now, the detector is the all-important thing, and it must have seemed like magic to be able to listen to music or voice using these fairly crude components and, as it were, extract the music out of the air. So what was the detector, and why was it so key to this technology? Well, this is what it looks like. This is the cat's whisker detector. It's not a cat's whisker, all right? You don't need a cat. It's a piece of wire. It's a piece of very fine wire with a sharp point, which you can see there. And it's in contact with a crystal of, in this case, lead sulfide, or galena as it's called. Other crystals would work. Silicon carbide would also work, commonly known as carborundum. And there were companies who produced these, and you could buy these. But to get it to do what it was supposed to do, that is, block current in one direction but allow current to flow in the other, it's what we call a diode, a point contact diode. And to get it to work, you had to find just the right place on the top of the crystal and push the wire just hard enough to make good contact. And of course you did this by listening as you were doing it. So there's a handle there where it says adjustable mount, and you waggled it around on a ball and socket joint, and hooray, you got the music, and you could hear Jimmy Shand or whatever it was. No, he wasn't born then. And then somebody bumped the table, and you would probably say something like, "Oh dear, what a pity," and start again, right? So it was a bit fiddly, to say the least. Now, why it was so important? Here we see three waveforms on this graph. The top waveform is radio frequency. This is volts up and down the way and time from left to right. And this would be at a frequency of about 500 kilohertz or a megahertz, a million cycles a second. That's what's called the carrier wave. And on top of that is imposed the sound wave. That is the music or the voice or whatever it is that you're trying to hear. Now that, as you know, is in the range of hundreds of cycles to thousands of cycles per second. So it's very, very low frequency compared with the radio wave which is being transmitted. And the combined waveform looks like the one at the bottom. And you'll see here that that shape on the top and the shape on the bottom is in fact the shape of the audio, the low frequency audio waveform. But if you just feed that bottom waveform into your headphones, you would hear absolutely nothing. Because the headphones don't respond to the radio frequency, they respond to the low frequency. And it's completely symmetrical. So at any time, it's equal, positive and negative. So what you have to do to be able to hear it is to lose either the bottom half or the top half. And that's what the diode does. So here we have the waveform coming in at the top, here. It's being fed through the tuning coils, which you can ignore just now, and to the cat's whisker detector, which is connected to the headphones. And what happens is, this allows current to flow from left to right, but blocks it in the other direction. So you lose the negative half of the signal, and the positive half you can hear in the headphones, as music or voice. It's as simple as that. The capacitor here is a filter to kill off the radio frequency. Now, there has to be a reasonably strong radio signal to give enough energy to produce an audible signal in the headphones, and that's why you need a very good aerial. And crystal sets did not work very well in Orkney. I'll come on to that later. But who do we have to thank for all the physics and electrical engineering that enabled this radio system to work? Well, for that we need to go right back to the middle of the 19th century to Michael Faraday. Now, Michael Faraday was a brilliant experimental physicist. He was an apprentice to Humphrey Davy. And as well as being a very gifted scientist, he was a gifted communicator. And he'd been working with magnets. Now, magnets are kind of spooky things if you think about it, because they can exert force on each other when there's nothing in between. Even if there's a vacuum in between, if there's a magnet there, a magnetic particle will experience a force. He realized that the same was true of electrically charged particles. And Michael Faraday came up with the concept of a field, a sort of aura that was around these things that extended out into space. And he called these lines of force. You can show the magnetic ones with iron filings on a piece of card. I'm sure you did this at school. And Faraday realized that to take this further, he had to be able to calculate the force on a magnetic particle or a charged particle at any point in space in 3 dimensions, and be able to say, yes, if it's there, the force will be so much. But this level of mathematics was beyond him. So he contacted a young Scottish scientist who'd come to Cambridge called James Clerk Maxwell. Now, fortuitously, Maxwell would turn out to be one of the greatest scientists who ever lived. And he looked at Faraday's results, all his experimental results, very carefully. And he came up with a mathematical expression for the force at any point in space around a charged particle or a magnet. He also went on to have a very distinguished career. This lecture's not about him, by the way, but I will just mention a couple of the things that he did. He did a lot of work on the human perception of colour. He was very much into light and optics. And he produced the first colour photograph in 1861. And he laid down the basic science of colour printing, colour photography, colour displays, which are still in use on your computer today, your digital camera, and so on. So Maxwell was an absolute star. Now, about 10 years after he did the maths for static charges and static magnets, Maxwell revisited this. This was about 1864 by this time. And in the meantime, he'd met and been in discussion with William Thomson, another physicist in Cambridge. And he was working on heat conduction. And Thomson, later Lord Kelvin, had concluded that nothing is static, that temperature of a substance, whatever it is a measure of the energy that's in it. The hotter it is, the more the atoms in that material are vibrating. And indeed, if you take a piece of material and heat it very, very hot, it becomes incandescent and it loses energy in the form of light. So Maxwell thought, well, these calculations that I did assumed everything was static, but nothing's static. Supposing these charges are vibrating. If the charge is vibrating up and down like that, the electric field associated with it can't be static, it must be dynamic. And another charge particle will experience a varying force, an undulating force as he called it. So definitely if electric charge is accelerating up and down, it will disturb the field, and that will be felt by anything else round about. He then realized that as well as a change in electric field, there would be a change in magnetic field, Because in Denmark, Ørsted had shown that a current in a wire produced a magnetic field enough to deflect a magnetic compass. If you reversed the direction of current in the wire here, the needle deflected the opposite way. So, there's a field, a magnetic field at right angles to the current. So, returning to these dynamic charges now, we have what's basically an alternating current with this electric charge going up and down. There must be an alternating magnetic field as well. And he thought, aha, could it be that there is an electromagnetic wave? And he spent a great deal of time producing a set of 20 mathematical equations, which would become known as Maxwell's equations, that described electromagnetic waves. He also calculated the speed at which they would travel through space, knowing these fundamental constants, epsilon naught and mu naught, which is the electrical and magnetic properties of space. And he came up with this absolutely humongous number, right? 3 times 10 to the 8 meters per second, or 300,000 kilometers per second, or 186,000 miles per second. So it's an absolutely mind-boggling number. But the key thing is that in France, a few years earlier, a gentleman called Fizeau had measured the speed of light in a very, very elegant experiment, which I'm not going to describe here, but it's worth looking up. And he got a number close to this. So Maxwell suddenly thought, wow, it looks like light is an electromagnetic wave, because this agrees with Fizeau's value. And this is what he said. It seems that we have strong reason to conclude that light itself, and he included radiant heat and other radiations from his discussions with Thomson, is an electromagnetic disturbance in the form of waves propagated, propagated through the electromagnetic field according to electromagnetic laws. And he published this in 1865. He didn't shout from the rooftops about it, but in a letter to his cousin, he said that he held it to be great guns. So that was the nearest he ever came to blowing his own trumpet. But we now know, of course, that the visible light part of the spectrum here is just a tiny part of an enormous range of electromagnetic waves that we have. The sun, as well as giving us visible light, gives us ultraviolet, which gives us sunburn, and infrared that gives us heat. And man-made radiation at the long wave end, all our radio transmissions, TV transmissions, and so on, have wavelengths in the order of meters and hundreds of meters. And at the short end, we've got gamma rays and X-rays and so on, which are also man-made. The relationship between frequency and wavelength is that the frequency times the wavelength gives the speed. Now, Maxwell died in 1879, but he did nothing about this experimentally before he died. But in 1886, this gentleman, Heinrich Hertz, decided he would try to prove the existence of what he called Professor Maxwell's electric waves. And to do this, he built this apparatus. And the part on the left here, if you've worked with old cars, as I have, you'll probably recognize that as the ignition system of a car. Of course, that had not yet been invented. This idea would eventually be used to fire the spark plugs in a car. But Hertz came up with this induction coil, which was in fact a Michael Faraday invention. So what happens here is, when we break the switch, the current collapses in the primary coil here, and there are many thousands of turns in the secondary coil, so we get a huge voltage induced in the secondary. And there's a spark gap here, and when the air breaks down in that spark gap, there's an enormous blue flash, and there is a very big alternating current that decays away, at a frequency set by the inductance and the capacitance that's around. Now these things were used as spark transmitters later. They're now illegal because what they produce is an enormous splurge of radio noise. They're not very selective in frequency. Now, Hertz thought, well, if I can do that, I wonder if I can detect the waves that are coming off the antenna here with something as simple as a loop of wire. And he thought, well, it'll be a bit feeble. He realized that. So he thought if he brought the ends of the wire very close together, maybe there'd be enough voltage induced in the loop to cause a tiny spark. Well, he tried it, and it worked. But the wee yellow spark there was so feeble, he had to use a magnifying glass or a microscope to see it, because the ends had to be almost touching. This was the only way he could detect the radio waves. Would you like to see that again? Okay. Now he was asked, what's the application of this? And he said, none whatsoever. But it does prove the existence of Professor Maxwell's waves. So Professor Maxwell was right. Now I find it hard to believe that he couldn't think of an application, because by that time, 1886, the electric telegraph had spread all over the world. The whole world had access to telegrams sent on wires. The Atlantic cable had been successfully completed about 1860, across transatlantic cable. And it was a very successful system. Basically, letters of the alphabet were sent as pulses along wires. And anyone skilled in the art could read the Morse code and write it out. This invention of Hertz was not lost on a lot of other people. One of them was Marconi. Now, Marconi was a businessman rather than a physicist, but he knew that he could send messages by a telegram to all the major ports in the world and the British Empire. But the big problem was, how did you get a message to a ship after it had sailed? Once it was over the horizon, that was it. You could not communicate with it. And he realized that wireless communication with shipping was a huge opportunity. And he set up a business empire based on that. By about 1901, he'd transmitted radio waves across the Atlantic, for example. And he set up a network of transmitting and receiving stations using simple spark transmitters and simple detectors. And these were text only. But he supplied the equipment, he also supplied the operators. And forever after that, radio officers on ships were called sparks. I think they still are to this day, although they don't use spark transmitters. But it was text only. There was no voice. And they had a big problem, is how did they detect the incoming radio signal? How could they read the Morse code that was coming in? And for this they used a device called a coherer, which I've got a diagram of here. It's a glass tube with two metal plugs in it connected to wires at the end. And in this little hopper between the plug, they don't touch. In this little hopper, there's a pile of metal filings, usually silver filings, silver powder. And in its normal state, it will not conduct electricity. If you connect it to a battery, nothing would happen. But if a pulse of radio frequency current comes in, it does a strange thing. The particles fuse together momentarily. In a very short time, they cohere or stick together, and then they will conduct current from a battery. So they devised a very clever circuit here, which will sound a clicker that they can hear. But when they first tried this, they found that it would work only once. Once the particles stuck together, that was it. They stuck together forever. But in the best engineering tradition, they thought, well, if we hit it with a hammer, will that fix it? So they hit the glass tube with a hammer, And that was enough to shake up the filings. And it was high resistance again, ready for the next incoming pulse. So this was a system that ran without any trouble, and someone could either write down or it could print dots and dashes on a piece of paper. And that's how Marconi built his empire. There was no electronics involved at all, a very simple detector. And he demonstrated, of course, that we could transmit over the horizon with long wavelength radio. He was operating round about a megahertz, hundreds of meters wavelength, and the ionosphere, which is a layer of charged particles in the atmosphere, acts as a mirror, so the signal from the transmitter to the receiver can bounce up and down off the ocean. Now, Orkney was in on this new technology very early on, as early as 1910, in fact. And this came about because there was a tragic shipwreck close to North Ronaldsay in 1908. A ship called the Isle of Arran was lost within sight of land. And they might have been saved if the folk in North Ronaldsay had been able to call the lifeboat. But in fact, news of the tragedy only came out days after in the form of a letter from one of the lighthouse keepers. And there was such a stooshy about this, it got all the way to Parliament. And in Parliament, they decided we need to fix this. But the channel between North Ronaldsay and Sandy was difficult to bridge with a cable. There was a cable, a telegraph cable as far as Sandy. So they decided, let's use this new Marconi technology. And they would install a Marconi set in North Ronaldsay in the post office, and also in the post office in Sandy. They balked at providing operators to live there. So they recruited the postal worker in each island. And in North Ronaldsay, it was William Scott. And in Sandy, it was Margaret Sinclair. And they were sent south to be trained at the Marconi School. And this radio link operated from 1910 until 1946, which was pretty amazing. Now, Willie became known ever after as Wireless Willie because he became what we would now call a radio ham. He modified the Marconi set so that he could listen to other things other than boring telegrams. And he used to pick up signals from as far away as Paris. He had a big problem because he didn't have a generator. And this meant that he had to have the chemicals for his Leclanche cells shipped in regularly on the steamer. Presumably, he eventually got a generator. Now, there's been a lot of what I would call key developments to enable radio to get where it is today. I'm not going to go through this list with you. You'll be glad to hear. I've indicated two there that I would like to talk about. The first is that in 1906, in Canada, a guy called Fessenden decided he would try to transmit voice and music on a radio wave, but he had no means of generating the high-frequency radio wave at high power. He needed power outputs in the order of kilowatts. And he decided he would use a high-frequency alternator, rather like the alternator that's in your car. The trouble is, if you try to speed up an alternator to get 50 kilohertz off it, it'll fly apart. It'll self-destruct. So he went for a special design of alternator with multiple windings to produce a high frequency at modest RPM. And he put it in the basement and surrounded it with sandbags and spun it up as high as it would possibly go without flying apart. And on Christmas Eve, 1906, he played Christmas carols on the violin and broadcast it as an amplitude-modulated signal. And it was indeed heard by friends of his who were primed to listen to it. But the key inventions that really made radio take off were the thermionic valve, the thermionic diode, and the thermionic triode in 1904 and 1907. And these really held sway for up till about the 1950s when transistors took over. The transistor was invented in 1947, the equivalent of the triode valve. And then in 1958, the integrated circuit came along, which just made things much smaller and lighter and lower power and so on. But I'm not going to go there because I spent most of my working life working in that sort of thing. But it's worth looking at the triode valve in detail because it really was the key component. It was based on electric light bulb technology, tungsten electric light bulb technology. And in fact, it was discovered by people who were trying to solve problems with tungsten filament bulbs blackening the envelope and so on. So inside the bulb, there are 3 electrodes. There's a cathode, an anode, and in between the two, there is a metal grid, a metal mesh. The anode is connected to a fairly high DC voltage, about 120 volts. The cathode is grounded. And if the cathode is heated, bear in mind this is metal, until it's glowing red hot, it will emit electrons, charged particles, and they'll be attracted to the anode. However, if a voltage on the grid is made very positive, it will attract more electrons from the cathode, so the current will rise. And if the grid is made negative, it will repel electrons and the current will fall. So a very small change in the voltage on the grid produces a much bigger change on the output. So we have an amplifier. We have a means of detecting small signals and making them bigger. Now this technology spread rapidly, and during World War I, the military were very keen on radio transmission, especially to ships, for obvious reasons. Again, during wartime, technology tends to advance very, very quickly. And the military trained thousands, probably tens of thousands of guys as radio operators, wireless operators. And they weren't just trained as operators, they had to understand it top to bottom and back to front and inside out because they had to fix it, it was unreliable. So these guys were really very, very good technically. And at the end of the First World War, a lot of them became radio enthusiasts. And before the BBC started, they applied for and were granted licenses to receive and transmit wireless messages. And 2 of these feature in the early days of radio in Orkney. This is the very first radio receiver that was built in Orkney, and it was built by James Sutherland, who's the postmaster in Stromness. It still exists, and it's currently on display in the Tankernes House Museum. But interestingly, it has a valve. So the signal for a crystal set was not good enough, so he had to add a valve to it. The second radio receiver was built by another First World War wireless operator, R.W. Korsch, who also worked at the Stromness post office. When war broke out in 2014, he had been a telegraphist in the post office, and he was immediately sent to Worcester and trained as a wireless operator. And after the war, he came back to the post office in Stromness. So he built the second set in Orkney. 60 years later, he was in correspondence with James MacDonald of the Wireless Museum. And he offered to send the Wireless Museum his training notes from 1914. And there they are on the right-hand side, his notebook. And I've gone through this, and I have to say I was amazed at how good it was. Here's an example. It's just a hand-drawn sketch of a transmitter. And if you look at the left-hand side there, the circuitry is almost the same as Hertz used in 1886. Now, the third set, sorry, I'm too close, I think. The third set in Orkney was bought by John Mackay. owner of both the Stromness Hotel and the Kirkwall Hotel. And Mr. Corsh, in a letter to James MacDonald, tells him the story of really the whole history of early radio in Orkney. And he said that John Mackay arranged a public demonstration of wireless technology in the North Kirk in Stromness. And it was duly all set up with extra loudspeakers and everything. This was arranged with the minister, Mr. Christie. And of course, with all technology, it doesn't always work first time, and they had a bit of faffing about to get it to work. And when it eventually burst into life, what came out was a drinking song. And the minister was incandescent with rage because he was a very strict teetotaler. But the town wasn't, set fire to with fire and brimstone or anything as a result of this. People latched on to radio, and it became a must-have gadget. Here's a picture of the first radio set in the Kirkwall Hotel in 1923. And it was sufficiently novel that it was photographed by Tom Kent. It was also noticeable that there are no batteries there, because by this time Kirkwall had mains power. Now, at the end of the First World War, there was obviously a demand for public broadcasting, because the companies, particularly the Marconi company, saw this as a business opportunity. And to drum up support, they arranged various test transmissions. They started doing things like reading the railway timetable. But then they thought, let's get Dame Nellie Melba, the best known opera singer in the world, and get her to do a test broadcast. And by this time there were thousands of radio enthusiasts around the country. So she agreed to do this, provided she had a slap-up dinner, and she was paid her usual fee, which was £1,000. This is in 1920, £1,000. So she had the dinner, and as they were walking across the yard to the studio, one of the engineers said to her, "Just think, Dame Nellie, in a few minutes your voice is going to be going out to the world from that mast there." And she said, "Young man, if you think I'm going up there to sing, think again." Anyway, she started with Home Sweet Home, and she finished with God Save the King, apparently. Now, they moved very quickly to establish transmitting stations once the BBC got going. The first one was the 14th of November 1922, the centenary that's coming up. But within days, they had stations in Birmingham and Manchester. And eventually, we had one in Glasgow in March 23. The British Broadcasting Company had been formed by 3 World War I veterans, Burroughs, Lewis, and Reith. There was an issue of controlling it, because in the United States, broadcasting had had a free-for-all, and there were thousands of commercial stations interfering with each other. And the British decided, no, we're not going to do this. We're going to have everything controlled by the General Post Office. And there will be licenses to have receivers and license to transmit. So they would control it. And the wireless license for each receiver was 10 shillings, or 50p, half of which would go to the broadcasting company to provide programs. And so on the 14th of November, Arthur Burroughs summoned up his best voice and said, "Hello, hello, 2LO calling," etc. So that was the first official broadcast. Now, Reith was the son of a Presbyterian minister, and he had very strong religious views. So everything had to be serious. And he said, "Whatever is done shall be well done." He insisted that the newsreaders had to wear a dinner jacket and a bow tie. This was on radio, remember? Nobody was seeing them, nobody at all, but it was just to get the right attitude. Of course, regional accents were out. It had to be a cultivated, received pronunciation accent. And they set out to educate, inform, and entertain, but Reith wasn't very keen on the entertainment bit. And the issue of government control came up, because in 1926 there was a general strike led by the miners. The government were very worried about public opinion, and they saw broadcasting as a way of, let's say, altering public opinion. So after the experience of the general strike, the British Broadcasting Company was effectively nationalised and became the British Broadcasting Corporation, but it was the same initials, so they didn't have to change the notepaper. But they didn't always get the programme content right, because they realised they had a tiger by the tail. If they said they were going to be broadcasting for whatever hours per day, they had to find something to broadcast. So they had serious talks, they had music, and all that sort of thing, religious services. But they didn't always get it right. And this is one from 1928. Someone wrote in to say, we want entertainment, not instruction. Cannot a meeting of protest be called? I'm afraid it would require a very large space. So they did have points of view and feedback even then. But radio spread very quickly all over the country, and indeed to Orkney. And this is a picture of my father's uncle, Henry Stevenson, who was the schoolmaster in Harry. He's wearing headphones. It's not a very good photo because of the light from the window, but he's wearing headphones, smoking a pipe. And over at the right-hand side there, you can see what I think is definitely a lead-acid accumulator, because of course, he did not have mains electricity. If we look at one of these sets, this is one from our museum in Burntisland. It has a horn loudspeaker, it has a frame aerial, a 4-valve radio receiver, and it requires 3 batteries. Now, this would have sold in 1926 for about 25 guineas, or 26 pounds roughly. That's a serious amount of money, because wages were about £2 a week or so. So it was a big investment, yet they sold very well. But power was a major problem. The heaters to make the cathodes in the valves glow red required about 2 watts for each valve. And the only way to do that was with a lead-acid accumulator, like a small car battery. You needed a high voltage supply, about 90 volts to 120 volts. And that was done by having just a whole lot of 1.5 volt cells in series in a cardboard box. But depending on usage, the battery powering the heaters, the accumulator, would have to be recharged perhaps once a week. And if there was no mains electricity, you had to go to somewhere that was a generator, usually the local garage or radio shop. The dry battery would probably last for 3 months, and the grid bias battery, which was simply used to set the operating point of the valves, it would last for years. Now, the heyday of wireless was in the 1930s. And this is Harry Matthews, the late Harry Matthews, founder of our museum, with a 1930s Murphy set. And alongside it is a very nice Bakelite round echo from about that era. But television appeared as well in the 30s. 1926, John Logie Baird had demonstrated a 30-line TV image, which was about the minimum number that you could recognize a face on. It was a fiendishly complicated mechanical scanning system based on a single photocell or a single light source. I'm not going to try to describe it. But TV test transmissions started about 1936, using both the Baird system and a competing system from EMI, which turned out to be far superior. But both systems were shut down on the outbreak of World War II. And World War II was really partly an information war, and this was realised by the government early on. But the radio manufacturers had all been turned over to manufacture electronics for the military. There was a shortage of electronic components, but they wanted people to have radio. And so they decided, let's have a utilitarian set, almost a sort of national set. And this is an example here on the left. It was a very basic 4-valve set, mains powered. It was medium wave only, and it sold for about £12. Now, we've got several of these in the collection, some of them in working order, and a few years ago we had one playing in an exhibition. It was tuned to 247 meters in the medium wave, which is Radio 1, and a young lady had been listening to this for a bit, and then she said, I didn't know we'd Radio 1 in the war. Now, after the war, TV transmissions had a kind of slow start, but it had a huge boost in 1953 with the coronation of Queen Elizabeth. Huge numbers of television sets were sold in advance of that. And the BBC really pulled out all the stops to do an outside broadcast in Westminster Abbey. They were walking on eggshells because they hadn't to offend the royals and they hadn't to offend the church authorities. And Richard Dimbleby was put in a box where he couldn't be seen, but where he could see the proceedings. And he did a marvellous commentary. And he was stuck in that box apparently for 5.5 hours, which is a tribute to his bladder capacity, I would say. Anyway, they reckon that they had 20 million people saw it, which was 40% of the country. Now, moving on to Orkney-specific things, Orkney got its own TV transmitter in 1958. Up till then, the signal had not been good. As you know, colour came in 67, and I've just written down a few of the what I regard as milestones, but you'll have your own favourite key moments that were televised. To do the coronation, they had to develop remote control cameras so they could have cameras sited where they couldn't have people. And it turns out we have one of those cameras in our collection in Burntisland. These are the masts at Netherbutton, wartime radar masts, which were used for the Orkney transmitter from 1958 to 1986 when it moved to Keeley Lang near Finstone. And from 1958 on, we could watch the test card when they weren't transmitting, because television programs were not transmitted all day then. 1977, Radio Orkney started. This is a picture of Liz Davies and Howie. Howie's here tonight. In 1977, I think if I hadn't put the date up there, you would have guessed it from the wallpaper. Now, finally, I would like to take you back to the first Orkney Science Festival. Now, what's this got to do with broadcasting, I hear you say? Well, it will become clear. The first Orkney Science Festival, Dave Renshaw and I did a double act in the Air Hotel. I described how we could make things very small using photolithography and interconnect millions of transistors on silicon wafers. David described a new device that he and colleague Peter Denyer had designed, which was a single chip video camera. Now, in those days, the smallest video camera was about half the size of a shoebox and cost several £100. This would fit in a matchbox and cost less than £10. They formed a company called VLSI Vision Limited, and within 2 years, there was a higher resolution, full color version of this camera available, which was adopted by mobile phone manufacturers. And the rest is history, as to say. A modern mobile phone has several single chip cameras in. It's usually got a low resolution one on the front for FaceTime or selfies, and it's usually got a high resolution camera. And these cameras are now so good that they can be used to give broadcast quality TV. So reporters in the field can use their phone to give live images of good quality and upload them for broadcasting. These cameras have also enabled things like endoscopes that can be pushed into parts of your body that you'd rather not look at, but the medics want to look at. Small battery-powered drones can carry multiple cameras and give very good quality images. There's a whole lot of applications like that have become possible. So this shows how things can change drastically in response to a technical development. So what about the future? Well, more and more of the young people do not watch BBC One television. They get their information and entertainment via the internet, and increasingly from their phone. In fact, a lot of people seem to have their phone clamped to their head or in front of them all the time. Could this have been predicted? Well, there are now billions of these devices on the planet, and we get immediate news if there's a major catastrophe, we can probably get an image of it right away. But there was a guy who was chief engineer of AT&T, the American telecoms company, and when he retired, someone asked him what the future might bring. And this is what he said, and I'll read it to you. Let us say that in the ultimate, whenever a baby is born anywhere in the world, he's given at birth a number which will be his telephone number for life. What a good idea. As soon as he can talk, he's given a watch-like device with 10 little buttons on one side and a screen on the other. Thus equipped, at any time when he wishes to talk to anyone in the world, he'll pull out the device and punch on the keys the number of his friend. Then turning the device over, he will hear the voice of his friend and see his face on the screen in colour and in 3 dimensions. If he does not see and hear him, he will know that the friend is dead. Now we're almost there, aren't we? Now I would like to ask you to guess. This is Harold Osborne, who was chief engineer of AT&T. I would like you to guess when he said that. The year or the decade even. 60s? Anybody else? Well, it was 1954. And at that point, I will stop. I've slightly overrun on time, I'm sorry. Thank you for coming. I would like to thank our online audience, if they're still with us, and also our technical team, who hopefully have kept the online audience connected and have made the whole thing happen.
That was absolutely fascinating, Tom. I got right into that again. It was just fantastic. We're going to take questions from the audience, so if you can look out for those. In the meantime, I'll just kick off. My great uncle and his neighbour friend in Brecon, they built their own crystal set somewhere in the early 30s. Now, they were just young men, but they were ordinary factory workers, weavers in Brecon. And I'm wondering where they would have found the information, the instructions, the equipment to build their set, because they had nothing to do with GPO or Army or anything.
I think by the 30s there were magazines for enthusiasts like Wireless World, and they published designs, and there were probably companies marketing kits of parts. And the things like the tuning coils could be wound by hand if you had the patience. You know, the core of a toilet roll and lots of wire, that kind of thing. And they could buy the crystals, the cat's whiskers assembly, and if they just needed a pair of high impedance headphones to listen in, and it would probably work if they had a good signal.
I remember him telling me stories about having to get the batteries charged, but I think what they did was it was like exchanging lemonade bottles. They got a charged one and the left one, something like that. Anyway, have we? Oh, here we go.
Neil.
Yeah, Tom, thanks for that. Fascinating as ever. So thank you very much indeed. I was wondering about the signal ident numbers. So 2 LO. Mm-hmm. So was there a 1 LO, and who designated and stuff like that?
I think that was controlled by the post office. I think it was rather like the radio amateurs now. They get a handle issued with their license, and I think that label came with the license to transmit from the Channel Post Office. I'm guessing here. I don't think there was a 1 LO.
Just wondering, Tom, if you knew when the first radio broadcast from Orkney was, because it was the St Magnus Cathedral Octocentenary, from the Kirkwall Hotel.
Was that 1937?
Yes.
Right.
There was the service that did the cathedral. They recorded that, and all telegraph communication outside Orkney was suspended for the duration of the service, so it could be recorded in London. and used as the morning service and the home service.
Wow.
But the night of the pageant, great pageant, they had interviews from the Kirkwall Hotel with all the Storer Clouston and all the people involved in it. So
Does that recording still exist?
I would greatly doubt it. It's probably live, but I mentioned there's only two of that performers from the pageant interviewed, and one was my great-great-grandfather, John Kirkness. And I think it's John Ferguson of Radio Orkney. It's a close relative. I think it was his father that was the engineer in charge of that.
Wow. That's a good story.
It certainly is. I was thinking, Tom, see in the Second World War, right? See the resistance fighters and things who were given radio sets and things. That couldn't have been a simple crystal set, especially not with a 90-metre wire, because you'd have been found, wouldn't you?
Yes.
So,
yeah. No, we have in our collection in Burntisland, we have a number of so-called spy sets, that went in a suitcase or whatever. Yeah. And yes, they were valves, and they could operate on almost any power supply. If they could find mains power, they didn't care whether it was AC or DC. They had the circuitry to cope with that, for example. But they could also use batteries. And we had a lecture at the museum from a former special agent who had been parachuted into Yugoslavia at night with his wireless set. And he told the story about how he had to carry batteries as well, lead-acid batteries, because they were in the mountains. There was no power there. And on one occasion, he had his 2 batteries slung on the back of a donkey. And the donkey fell off the cliff. So he had no batteries. But when he got to where he was trying to operate, they spotted a German lorry. The German lorry rapidly lost its batteries, and he was able to continue. Now, this guy, sadly, he died a few years ago, but he a more unlikely special agent you would never imagine. After the war, he'd become a carpet salesman and a furniture salesman, and he was just an ordinary, lovely old guy, but he had this amazing background.
That's probably what made him the ideal special agent, of course.
Exactly, yes.
Did they have broadcast on exactly the same channel every time, or
no?
No, that's
no. All that was for security reasons. You're inviting trouble if you transmitted on the same frequency the next time. But they had as it were, a book at their end and at the receiving end. So each day they had a different set of settings.
Cool. I always wondered that, actually. Is there any more questions? Oh, there's one up there, yeah.
If you'd all come to afternoon tea this afternoon in the Peacock, you'd have heard me talking about a family story I had of my about the Crimea. And my father's great aunt was born in the Crimea in 1850, and Russian was her native language. But she came to live in Britain after that, as a small child, but she could still remember. And my father always said to me that he remembers her. She died in 1947, aged 96. He could remember her listening on her crystal set to the Russian radio. Is that really possible? Confirm whether, please, was he telling me a load of rubbish or not? But he always said that he could remember her great aunt Sis listening to the Russian radio on her crystal set in her 90s.
I think that's possible, especially if it was long wave. It's a kind of fact of physics that long wavelengths tend to travel much further than short wavelengths. And if the Russians were broadcasting on maybe 1,500 meters or something like that, and she had a long aerial, it would probably work, yes. Someone right up the back.
Just right up the back, yeah.
Do you know anything about the radio transmissions for THTC meters?
In a word, no. Sorry. But we do have in the audience Dr. Spence, who may be able to help out on this one.
I'm afraid I can't help either.
He can't help either. Sorry, failed.
On a sort of slightly different but related topic, my father was a radio ham that you mentioned, and self-taught, although he had to get his qualifications at Dundee Tech. Golf Mike 4 Tango India Yankee, I still remember his call sign. And he loved using 4-watt Morse key. And he used to skip the atmosphere to try and get... He worked for the Americans at RAF Edsel, and they had a Radio Shack, and they used to try and get the USSR countries to get their QSL cards. It was quite interesting, yeah. Any more questions at all? Okay, Tom, I think we're going to end it there. That was absolutely wonderful. Thank you to the audience for submitting your questions. Thank you to the online viewers submitting your questions via Slido. And can we please thank Tom in the usual way, please? For festival goers here in Orkney, our next talk is live in this theatre starting at 7:30 p.m. It's the Mary Beath Lecture, and it features ecological gardener Elizabeth Woodcock talking about a different kind of garden. The next online event begins at 9 p.m. and is the Caroline Wickham Jones Memorial Lecture called Rising Tides. Don't forget to like us on Facebook, Twitter, Instagram, and please subscribe to our YouTube channel, not only to get access to the events for this year, but to keep in touch with us throughout the year until next year's festival. Once again, thanks to Tom, and can I also thank the technical team who work silently in the background to bring you the Orkney International Science Festival. So thank you all very, very much.